Solubility is a very important physical and chemical property of a compound, and understanding the solubility concepts correctly will help you to properly understand the concepts and logic behind many of the other techniques that we will be using during organic chemistry synthesis. We call the substance to be dissolved as the solute, and this solute could be a solid solute or a liquid solute. And the dissolving medium is called a solvent. By solubilizing a solid or a liquid solute in a solvent will give us a mixture which we called a solution. We need our reagents to exist in a solution in order to follow organic reactions. And most techniques in organic chemistry needs for the compounds to be in some sort of solubilized form. That is why we have this lab as our first lab for the class, and the concepts you learn through this lab will be the base for all the organic chemistry techniques you will learn this semester. First, we will look at the solubility of a solid solute in a solvent. The solubility of a solid solute in a solvent can be given as grams per liter or milligrams per milliliter. In a standard test for solubility, we will mix 40 milligrams of a solid compound in 1 milliliter of a given solvent, and then we observe if the compound completely dissolves, partially dissolves, or does not dissolve in the given solvent. As an example, we have solubilities of cholesterol, caffeine, and citric acid given here. The solubility of cholesterol is extremely small that it's barely soluble. So we conclude that as insoluble in water. Citric acid can be soluble up to 620 milligrams in 1 ml of water. That's way more than 40 milligrams. Therefore, we call it completely soluble. However, caffeine solubility in water is 22 milligrams per milliliter, so it's only partially soluble. So these are the terms that we use to describe solubility of a solid solute in a solvent. It's either insoluble, partially soluble, or completely soluble. Now let's look at the terms that we use for the solubility of a liquid solute in a solvent. When we mix two liquids and they completely mix with each other, forming just one layer of liquid, we describe them to be miscible. Homogeneously means that they mix with each other to form a uniform solution. And this one layer of solution is also called one phase. When we mix two liquids and they do not completely mix with each other, forming two layers, we describe them as immiscible. We can also call the two layers as two phases. And heterogeneous means the solution is not uniformly mixed. Later in the semester, you will be learning about the extraction technique, and in extraction, we mix an organic liquid like ether with an aqueous liquid. Aqueous means water-based liquids, so an aqueous liquid like water. Since they are immiscible with each other, they will form two layers. Whichever liquid has the higher density will be heavier and it will be in the bottom layer. In this example, water has a higher density than ether. So water will be the bottom layer and ether will be the top layer. In extraction, we will identify them as the aqueous phase and the organic phase. So this is something that you will touch again later when we come to the extraction lab. Although we are not factoring the effects of temperature on the solubility in today's lab, I still want to mention it so you guys are aware of it. The temperature can change how soluble a solute is in a given solvent. A compound that is insoluble in a given solvent at room temperature could display increased solubility in the same solvent at a higher temperature. As an example, let's take a look at dissolving sugar in water at different temperatures. It's really difficult to dissolve sugar in ice cold water, but it's somewhat soluble in room temperature water, but then highly soluble in boiling water. This is because heat provides the energy necessary for the sugar molecules to become more soluble in water. And this is why we see a higher solubility with the increasing of the temperature. And this concept will be important when we do the recrystallization lab. And I will mention that again during that lab, and we will revisit and discuss this concept in more detail. The solubility of a solute in a given solvent depends on how well those solute molecules can interact with the solvent molecules. If they can form favorable interactions with each other, that solute will be very soluble in the solvent. If the solute molecules and the solvent molecules can't form any favorable interactions, then that solute will not be soluble in the solvent. Let's take a look at the different types of interactions that can exist between molecules. Since these are interactions between separate molecules, we call them intermolecular interactions or intermolecular forces. First, we have ionic interactions. These are interactions between charged groups. For example, when a sodium atom and a chlorine atom form sodium chloride, the sodium is going to lose that one electron it has on the valence shell, making the sodium atom a positively charged ion. Chlorine will accept the electron from sodium and it will become a negatively charged ion. And we know that opposite charges attract. And once when these atoms are charged, we call them ions. And this charge attraction between the ions is called ionic interactions. This is the strongest type of intermolecular interaction. Then we have something called the dipole-dipole interactions. I'll go back to this hydrogen bonding. I'm going to first talk about dipole-dipole interactions. This happens when we observe a significant difference between the electronegativity value in two atoms participating in a covalent bond. So what exactly is electronegativity? It is the ability of a nucleus of an atom to pull electrons towards itself. So atoms like oxygen, nitrogen, fluorine have very high electronegative values. In this example, oxygen is sharing electrons with a carbon. So it's forming a double bond with this carbon. Oxygen has an electronegativity value of 3.44 and carbon has an electronegativity value of 2.55, which is much less compared to oxygen. So oxygen is able to pull the electrons that it's sharing with this carbon more towards itself. So this bond is actually going to be polarized towards oxygen. The electron cloud flowing around this oxygen and carbon bond is going to be polarized more towards oxygen. Since electrons are negatively charged, this causes a partial negative charge on the side of oxygen and a partial positive charge on the side of carbon. And this polarization is kind of permanent because oxygen is always electronegative than carbon, right? So this polarization of the electron cloud is permanent, and these poles or these dipoles can interact with other oppositely charged dipoles. Similarly, this bond is also polarized, giving a small negative charge towards oxygen and a small positive charge towards carbon. And these oppositely charged dipoles attract each other, and this is what we call as dipole-dipole interactions. Hydrogen bonding is a specific class of dipole-dipole interactions. It has been given its own name because it's a more specific form of dipole-dipole interactions. Hydrogen bonding exists when we have molecules where an oxygen, nitrogen, or fluorine is sharing a bond with hydrogen. The electronegativity of hydrogen is, the value is 2.20. So the difference in electronegative values come between oxygen, nitrogen, fluorine, and hydrogen is even higher. So this gives these bonds an even stronger polarization. For example, in water molecules, the electrons are strongly polarized around oxygen. So this gives a partial negative charge around oxygen and a partial positive charge around hydrogens. And these oppositely charged dipoles are able to interact with each other. Oh, sorry, that was wrong. Dipoles here. And this is how the water molecules interact with each other and form these strong dipole interactions to hold them together, making it exist as a liquid at room temperature, all the way until it boils at 100 degrees. So these interactions, these dipole-dipole interactions involving hydrogens bonded to an oxygen, nitrogen, or fluorine, we give it this specific name called hydrogen bonding. So ionic interactions is the strongest, hydrogen bonding is the second strongest, dipole-dipole interactions other than hydrogen bonding are the next strongest type, and the last type of interactions is van der Waals interactions. There are some classes of molecules like hydrocarbons where the electronegativity difference between the atoms participating in a particular covalent bond is negligible. For example, the electronegativity difference, let's say it's a carbon and a hydrogen, the value for carbon is 2.55. The value for hydrogen is 2.20. So this difference is very negligible. Therefore, the electron cloud is not going to be polarized towards either atom, and it's going to be evenly distributed. This type of molecules depend on spontaneous changes in the electron cloud to induce temporary dipoles which can attract neighboring molecules. That happens because these molecules, there are millions of molecules in a given solution or a gas, and they can bump into each other, right? When they collide into each other, that can cause a temporary change in the electron clouds, causing these temporary dipoles to form. These are called induced dipoles. And there can be some attraction between these spontaneous dipoles. Although they are not that strong, and we consider them the weakest type of intermolecular forces, but when you have millions of these molecules in a solution or a gas, there is strength in numbers. When there are so many of these bonds forming and breaking and forming and breaking simultaneously, it's strong enough to hold them together. So always remember the order of strength for these type of intermolecular forces. Again, the strongest is ionic interactions, next strongest is hydrogen bonding, then the normal dipole-dipole interactions, and van der Waals forces are the least strong type of interactions. There is, however, another type of interactions where ions and dipoles can interact. We call it the ion-dipole interactions. And the strength of this is probably between ionic interactions and before hydrogen bonding. And this is how salts can be solubilized in water. The partial negative charges of oxygen in water molecules, so oxygen is given as the red circle, and the two hydrogens of water are given as the white circles here. The partial negative charges of oxygen in water molecules can interact with the positively charged sodium atom, and that interaction helps solubilize sodium ions in water. Sodium is inorganic, but what about an organic molecule carrying a charge? If an organic molecule has a true charge, then it can form ionic or ion dipole interactions with aqueous solvent molecules like water, and because those interactions are much stronger, they can become soluble in a polar solvent like water, even though if they have a hydrocarbon part in the molecule. So remember, for this class, if you're given an organic compound that has a charge on it, it can be solubilized in aqueous solvents like water. There are some exceptions, but you don't have to know that for this class. For this class, remember, if an organic molecule has a charge, it's definitely going to be soluble in aqueous solvents like water. Now we're going to go over guidelines for predicting polarity of molecules. It means, how do you know if molecules have poles or don't have poles? In other words, are they polar molecules or else non-polar molecules? First, all hydrocarbons are nonpolar because they're made of carbon and hydrogen, and they don't have a significant difference in electronegativity values. The electronegativity of carbon is 2.55 and the electronegativity of hydrogen is 2.20. So when there are bonds between carbon and hydrogen, there is no polarization of the electrons shared between them. They're going to be evenly distributed. So these type of molecules interact with each other only through van der Waals forces. So the same here. So all of these bonds are non-polar bonds. So There is no polarization existing. That means all hydrocarbons behave as nonpolar molecules. Then we have organic molecules that have a short carbon chain. That is, they have a carbon chain with 4 or less carbons, and if they also have a highly electronegative atom like oxygen or nitrogen, those molecules are considered polar molecules. The strength of these dipoles overpower the strength of the van der Waals interactions of these nonpolar parts, so they're able to carry these short carbon chains into polar solvents by the strength of the dipole interactions. Also, if any of those oxygens or nitrogens are bonded to hydrogens, then they're able to form the stronger version of dipole-dipole interactions, which is hydrogen bonding. So whenever these kind of bonds exist with a short carbon chain, those molecules are considered as polar molecules. However, if the length of a carbon chain is greater than 4 carbons, then the polarity from an oxygen or a nitrogen is not sufficient to carry them into polar solvents. When the chain of the hydrocarbon part gets bigger and bigger, there is more and more chance to make van der Waals interactions. That means those molecules become less and less polar. So as an example here, we're looking at some molecules from the same family. These are all alcohols, and they all have an OH bond. And although this OH bond is polarized and is able to make dipole-dipole interactions, the longer the carbon chains become, the ability to make van der Waals interactions increase, and the ability of this polar OH to carry it into a polar solvent becomes less and less. In other words, the non-polar characteristic becomes more dominant as the length of the carbon chain increases, and it overpowers the ability to make dipole-dipole interactions by this OH group. Remember, polarity is always going to be described as a relative property. For example, relative to methanol, pentanol is more nonpolar. Relative to pentanol, ethanol is more polar, likewise. So if you're given 2 molecules of the same family, the one that has a longer hydrocarbon chain would be the more nonpolar molecule relatively. Here is a special circumstance you guys should remember. When halogens exist in organic molecules, do they contribute towards polarity? Fluorine has the highest electronegativity value from all the atoms in the periodic table, but the other halogens like chlorine and bromine are not that electronegative. They are more electronegative than most atoms, but then they're not able to induce a significant polarity in the bonds that they share with carbon. So hydrocarbons with halogens like chlorine and bromine are considered nonpolar. And what is the reason for this behavior? Let's use chlorine to explain. It's much larger atom compared to oxygen, nitrogen, or fluorine. Let's say fluorine has only 3 electron shells, right? But chlorine has 1s2, 2s2, 2p8, 3s2, and 3p7. right? So chlorine is a much larger atom, and when they form a bond with another atom like carbon, the distance between carbon and the nucleus of fluorine is much smaller compared to the distance a bigger halogen like chlorine would have with carbon. So the effect of its electronegative property is felt much less by the carbon than how it would feel it if it was connected to a fluorine. That's why these bonds around chlorine and carbon or bromine and carbon are not polarized, so they are mostly non-polar. Therefore, we consider these organic halides, including chlorine, bromine, etc., to behave as non-polar molecules. Now let's look at the solubility of organic acids in aqueous solutions. Acids are molecules that can donate a proton, a hydrogen atom. Simple organic acids like acetic acid are readily soluble in water, but how about acids that have a larger hydrocarbon part? We're going to use benzoic acid as our example. Benzoic acid is insoluble in water at room temperature because although it has these polarized bonds, it also has this large six-membered aromatic ring which is nonpolar. So the strength of the dipole-dipole interactions from the polar bonds is not going to be strong enough to carry this nonpolar part into an aqueous solution like water. So when you mix benzoic acid with water, the result is insoluble. However, if you mix benzoic acid with a base, an acid-base reaction will happen. The acid will give away a proton, and this base will accept that proton and create water, and benzoate, which is an ionic form, so it's the conjugate base of this organic acid, and you can see that it has a true charge. That means it can participate in ionic or ion-dipole interactions and become soluble in water or other aqueous solutions. Just like we discussed earlier when I talked about ion-dipole interactions, whenever an organic molecule has a true charge, it is strong enough to carry the whole molecule into an aqueous solution. So you will see that we use these acid-base reactions as a way to manipulate organic acids to become water-soluble later in the semester in extraction lab. Let's see if it can be soluble with an acid like HCl. An acid will not react with another acid because they are both proton donors and there's nobody to accept protons. So there will be no reaction and the outcome will be the same as trying to dissolve benzoic acid in water because HCl is an aqueous solution, a water-based solution. So the result will be insoluble. Now we're going to look at organic bases. A base is a molecule that is able to accept a proton. Usually organic bases have a nitrogen-based functional group, and this is called aniline. It's an 6-membered aromatic ring with an NH2 group, and you see nitrogen has this lone pair that it can use to accept a proton from an acid. So if we mix this aniline with water, it's insoluble because although NH2 itself is a polar group, it's not sufficient if the dipole-dipole interactions or hydrogen bonding this NH2 group can participate in is not strong enough to carry the 6-membered hydrocarbon ring into an aqueous solution, so the result here is insoluble. If we mix this organic base with another base, nothing will happen because there is nobody to donate a proton, so the outcome will be the same as trying to dissolve aniline directly in water. So it's also insoluble. However, if you try to react it with an acid, now this nitrogen can accept this proton from HCl and now it has 3 hydrogens and a positive charge. We have chloride ion here. Now it's an organic molecule with a true charge. So this conjugate acid form of this base is able to become solubilized in an aqueous solution. And this will also be a way we manipulate organic bases to become water soluble later in the extraction lab. Now these are the objectives I hope you all would be able to understand once you finish working on this lab. If you were given structures of a molecule, you should be able to determine the polarity properties of that molecule, determine whether a given liquid is miscible or immiscible with another solvent, correctly compare polarity properties between compounds within the same family like we did for alcohols, able to describe the different types of intermolecular interactions and how they contribute towards the solubility of solid and liquid solutes in a given solvent, demonstrate by writing a chemical reaction how water-insoluble acids can be manipulated to become water-soluble by reacting with the base, or also for a water-insoluble base, how can we make it water-soluble by reacting with an acid? So these are the objectives you should be able to explain once we have completed this lab. In the next few slides, I'm going to go over some of the experiments for this lab for all the part A, B, C, and D. And for some of them, I have only like a couple examples taken, but for example, in part A, there are actually 3 tables, but I'm only explaining 2 of them here, so you know how we're going to work on this. And in part A, what we're doing is trying to see the solubility of solid compounds in these 3 types of solvents: water, methanol, and hexane. We know the structure of water, and we know it's a very polar solvent. Methanol has a carbon chain of just 1 carbon and the OH group, so it is also a very polar solvent. Hexane, on the other hand, is just 1, 2, 3, 4, 5, 6. It's, oops, sorry. 1, 2. It's a completely hydrocarbon molecule, so there is no polarization, and therefore hexane is a nonpolar solvent. Once we've determined the polarities of each of these three solvents, now we're going to look at the polarities of each of these solid compounds that we're going to try and dissolve in these solvents. Benzophenone, you can see there are these two 6-membered rings which are nonpolar, but it also has this carbonyl group which is polar. So this molecule has both nonpolar as well as polar properties, so it's going to be intermediate polar. And you can, based on the concepts that we discussed, you can predict whether it will be soluble in water, methanol, or hexane. Since it has these large nonpolar groups, it's probably not going to mix well with polar water. So the observation would be insoluble. It would mix much better with methanol because methanol has the CH3 part which can form van der Waals interactions with the nonpolar parts of benzophenone, and the OH group which can interact with the carbonyl group to form dipole-dipole interactions and hydrogen bonding, so it's going to be more soluble in methanol. In hexane, it can form van der Waals interactions with this nonpolar aromatic ring, so that is also going to be mostly soluble. And in the discussion part of the table, you'll be explaining why you see this observation. Why are they insoluble? Because water is a polar molecule, and then you can explain the polarity of benzophenone and whether they form favorable or whether they are able to form favorable interactions or not, and then that would explain your observation. Malonic acid, on the other hand, we have an OH group here, carbonyl group here, carbonyl group here, and another OH group here. And the carbon chain is very short, only 3 carbons, right? So less than 4 carbons in the carbon chain plus all these polar groups makes it a very polar molecule. So it would be more readily soluble in water, soluble in methanol, but insoluble in hexane. That is our prediction based on the concepts we learned. Then you can watch the demo video for the experiments and see if your predictions align with the observations. You can note down your observations, and here you can discuss what is the reasoning behind the observations that you saw. In part B, you'll be looking at the solubility of different alcohols in either water or hexane. So water is polar, hexane is nonpolar, and then we have these two alcohols. Methanol has a carbon chain that is less than 4. Octanol means there's 8 carbons, so the number of carbons is greater than 4 for octanol. And we discussed the more and more longer the carbon chain is, it becomes more nonpolar. So the nonpolar property is higher in octanol versus methanol, which behaves more like a polar alcohol. So we would expect this polar alcohol to be readily soluble with water, but not so much with hexane. It might mix a little bit because it has this CH3 part in the molecule, but for most part it will not mix with each other. Versus here, one octanol, since the nonpolar part is more dominant, it will be insoluble with water, but it should be soluble with hexane because hexane is a nonpolar solvent. So these are our predictions. Then you watch the video, compare your predictions with the observations, note down your observations, and then you can explain why, what are the concepts, the reasons behind those observations. In part C, you are looking at the miscibility or immiscibility of given solvent pairs. So we have water with ethanol, water with diethyl ether. If you don't know the structures of these molecules, just look them up on Google and then look at the structure and determine whether they're mostly polar or non-polar or intermediate polar. Then you can determine whether it will be miscible or immiscible with the other solvent pair. So if they're of the same kind, if both solvent pairs are polar solvents, then they would be miscible with each other. You can also describe this as like dissolves in like, and like does not dissolve in unlike. That is, let's see. In this example, water and hexane. Water is polar and hexane is nonpolar. So they are unlike from each other. So they should be immiscible. That means they do not mix with each other. So you first predict your expectation, then watch the experiment video, make note of the observations, and then you can explain why you saw this observation. In part D, you will be looking at how an organic acid can be solubilized in aqueous solutions. So here we have that benzoic acid, and you will measure benzoic acid into 3 test tubes. Into one, we add water. Into another one, we add 1 molar sodium hydroxide. To the third one, we add 1 molar HCl. And as we discussed earlier, there is the 6-membered aromatic ring. So it's a large nonpolar part that causes it to become insoluble in water. And when we mix it with an acid doesn't react with another acid. So this is simply same as trying to mix benzoic acid in water. So we see it be insoluble. But when we mix it with a base like sodium hydroxide, those two are going to undergo an acid-base reaction, and we are converting benzoic acid into this ionic form, which can form ion dipole interactions with water, so it becomes soluble in aqueous solution. Then we take this test tube and add 6 molar HCl to it. What happens is the sodium benzoate becomes protonated by this HCl, and it forms benzoic acid again. Now it's no longer an ionic molecule. It was reverted back into its original form. So that means it's no longer soluble in aqueous solution. Therefore, it will precipitate out of the solution. And that is the observation you're going to expect. And the reason we added 6 molar HCl, unlike before we used 1 molar base or acid, you can see that we're using 6 molar HCl here. And the reason is we need a sufficiently concentrated acid in order to neutralize leftover base solution and then we need enough to protonate the sodium benzoate back into benzoic acid. So that is the reason for using a higher concentrated acid solution. That is all I wanted to explain for this lab. I will be having office hours on Friday, 8:30 a.m. to 10:30 a.m. and I'll post the WebEx link for that on Canvas. So if you have any questions, please join for the office hours. And if you can't make it on that time, email me or reach out to me to let me know if you need me to arrange a different WebEx meeting to discuss any problems you might have. Thank you.